Hey. Great. Comes in on so we hey why I turn around. Statistical errors, but right.
I'm well, how are you?
Good, thank you. So it's still. I thought it would be empty class because everyone would travel to do the long weekend, but I'm happy to see.
Wouldn't miss it.
Attendance above expectations.
It's
fine.
How do you think of what? You know, actually. Not really wrong, that's.
Curtis, Curtis,
Oh, why?
One has someone's like there. Thank you pretty much. What are we going to do today? No idea how to stick in all plant materials into one lecture and keep it interactive style, but I'll try my best. Maybe today there will be a little less interaction just to cover materials. So we do have an important administrative task to practice democracy. At the end of semester, we need to. I need to have some reasons to put grades into the system. I need some of your achievements to be recorded. So let me suggest that we will have a series of presentations in a week from now. Maybe 4 minutes per person, and they will be counted as a like midterm stuff like this. So there, by now we didn't went too much into math and problem solving. So it will be not about problems, but more about what we had as a discussion as a philosophy of quantum theory. And there are subjects related to this thing. They are often listed, mentioned as postulates of quantum mechanics in the textbooks, and they are so vague and differ so much from different textbooks that I decided not to present them myself and let you to do this hard work. But any effort in this activity will be generously credited. So we need to start speaking on the subjects and express your opinion, same as we did during discussion sessions. So the main task, well, I cannot say it is main, but one of the main tasks for today is to practice democracy and select which subject each of you would like to present in a week. There is nothing to be worrying and nothing to have stress about. So it is quite an easy thing. I will show briefly those postulates. Some of them are just 2 lines of text. So how to expand 2 lines of text into 4 minutes presentation, it is a challenge. I support it, I disagree, it is strange or look for additional materials. Since we have total count of postulates in different textbooks goes between 5, but some textbooks go 4 or 6, and we have 9 people in the class plus 1 auditing person. So I suggest to add a few basic chapters from linear algebra just to mention that they do exist. So we cannot do a lecture on some material in 4 minutes, right? And I'm going to go over the subjects on the board, and then there is a sign-up form in the online. But if you don't have a notebook with you today, you can just come to the central podium and then try it. So this is like administrative thing, and then we'll do the rest of the previous lecture and start new one, having a goal to introduce evolution operator and Schroedinger equation. And you just speak as much as I can about it. we know that we need to fit the schedule and do important material, but I'm looking for any excuse to avoid my primary task. And if you have some more fun of discussion sessions, questions about the class or not about the class, I will be really provoked to just have a visit chat. So, here is the summary of basically what we need to present within 50 minutes. You see, just 2 pages of text. It's not much. And there are 6 of them, which is less than an amount of activities in the class. So I suggest to chop them as first 6, and then additional 4 will be the how to multiply matrices, which probably everyone knows, but we will better recite. Another one is how to find eigenvectors of matrix, because it is a subject that we will use over and over again. It is important part of the class. Connection of Schrödinger equation to evolution operator is basically what I'm going to present today, but someone may share a vision or share disagreement or additional support. And concept of commutation of operator that I'm going to cover today as well. Someone can go deeper with this. So how can we arrange it? There is a link that I did send to everyone in the email with the slides. And if one goes to the slides, you will see this list of subjects and list of class attendees. So I suggest you may just connect your name with the subject by an arrow, which could be the simplest way. Okay. If you do not like to do it electronically on your seat, you can just come to the podium and mark it on your own here. So I think it is quite open and democratic. So you select subjects. If there will be more than one volunteers for the same subject, I will mitigate the conflict. And I will open them after we finish the class or during the weekend, and then send a finalized schedule. It would be very much appreciated if you send me the slides by the midnight of before the presentation. So coming Thursday midnight. And if I will be missing some of them, I will send friendly reminders coming closer to the deadline. Huh? Line, you see there is a line arrow, so you can do something like okay, so please play with it to your paper. Oh, this flash camera also allows to this spy camera from the back. Oh. It happens.
It's not where it is.
Reasonless. So, there is the subject that we are covering in this class was very generously awarded by I need to show myself. I get this. Look, how you take this from here, or swap between cameras from time to time. So this material that we are covering is a foundation of modern STEM science, and it was generously awarded by so-called Nobel Prize, right? So in some sense, we can call our class history of Nobel Prize in 20th and 30th. So each of these prizes can see the material that we are covering in this class, and it is foundation for physical chemistry. So Prince Louis de Broglie, the first one, just was philosophically analyzing the concept of electron as a wave. The Raman, some of you do Raman's scattering experiment, or you have.
I haven't yet.
Or you introduced to the box and told them this is the Raman spectroscopy instrument. Garrett, this is Raman instrument. Raman instrument, this is Garrett. This experimental technique provides evidences that nuclear vibrations are quantized, and we will cover it closer to, well, in the second part of the course. Heisenberg was, one cannot put them in a row and say who is more important, but the last three, they provide a different view on the quantum nature of electron, and they derive different mathematical tools to process them. So most intuitive and simple one is Schrödinger equation that we need to cover today, but there is a alternative formulation of quantum theory done by Heisenberg, which is a little less natural, but we will also mention it maybe in a week, maybe a little after your presentations. And Paul Dirac did many good things, but one of them that we will immediately use in the class is he designed a way to unify our thinking about mathematical continuous functions and vectors. So he designed an object that can be either vector or function at the same time, and it is very useful to what we plan to do. There is no reason for this slide; it's only to show that it's done by humans for humans. I'm not going to read out loud, but the best way to get through some subject is to get an idea what a designer of the subject was thinking himself or herself. So here is a quote from introduction of the book by Erwin Schrödinger, what he thinks himself about his equation and how he came to these ideas. So he's trying to do things that we were discussing, like connect ray optics, which we know that electromagnetic radiation is a wave, but in a limit of distance much longer than wavelengths, one can think that ray goes just by a straight line, and he makes connections to the electrons. In this brief preface to the book, he summarizes all concepts in more human language, which is always missed in classes like this. It is very natural to hate the quantum class and the instructor. Well, I'll try an effort and hope you'll do better than average because the subject is very counterintuitive. And the standard way of teaching the subject is going directly into math equations without trying to avoid any human formulations. But this is a rare piece of text where quantum theory is explained without equations. So you can just look through and get some ideas how it was developed and what the developer was thinking about. There are a few other handouts that I distributed. They're very optional. You can success with guarantee in a class without even opening them. But if you have nothing to do, check it out. You can open and look through them for another human words. And if we take standard text PChem for undergraduates, those words and those quotes will not be there. And it is always better to look not for like instructor or textbook retelling stories, but what the original developer was thinking about. So here is what we target as a goal, right? Here is where we stopped. So if one takes the absolute value squared or conjugated of the wave function multiplied by itself, it will be a probability distribution so that electron can be found in the interval, in the small interval from x to delta x, so it is just area. And if one integrates this function from minus infinity to plus infinity, it should be probability that we do have an electron elsewhere, which should be 1. So, question, and I will seek any opportunity to go to interactive style, which is much better. I'm just worrying to squeeze material, but here is the equation that James, and I correct his name, James, was asking question last time. So the equation on the top is not correct, and we are not going to show it. It's only for bringing in the concept. And action is the integral from for classical path trajectory for classical electron going from initial point of time to final point of time, where we do know the trajectory, how position changes over time, integral of the Lagrangian, which is kinetic minus potential. And again, not as a rigorous equation. Generally, through analysis of Bohr model, through some discussions, common sense, philosophical agreement and matching between concepts, we can assume, we can believe that if one knows wave function at the initial point of time, one can assume that from point in space x to point of space x prime, there is a trajectory. A trajectory can be associated with action, and this action will bring us from the past to the future. So this imaginary exponential with action as a power brings us from the past to the future. And this notation means that any position in the past is connected by any position in the future by a trajectory that one can compute by using like classical mechanics. If one knows forces, potentials, kinetic energy, mass, and stuff like this. So there is a convention. Since we are going from past to the future, the electron, its distribution evolves. So it is evolution in time. And this is an operation to progress forward from past to the future. So the common name is time evolution operator. Operation. And this is a key concept that we will use almost every day, and especially in our labs that will start from Wednesday after the Labor Day. There is a thing that I was trying to understand, but I cannot.
So if you find, I even have some papers and references that I found, but I still do not believe it. But if you find and bring it, mention it in presentation, or just give me a little hint personally, I will appreciate it. So the question is that all philosophical descriptions deal with action and with Lagrangian, which is kinetic minus potential. But at some point, which is skipped in all textbooks, the narration jumps from Lagrangian, from kinetic minus potential to kinetic plus potential. And they tell, oh, nothing will change. We will just, in evolution operator, we will replace everywhere where we had Lagrangian, we will have Hamiltonian. And nothing will change, everything will be as efficient as it was. I'm very against it, but it is what the rest of scientists in the world are doing. So if you find a justification for this step, it will be an interesting point of discussion. If we want very near future, if you propagate wave function on the delta t going to 0, then the integral can be replaced by just product of the value of Hamiltonian at given time times time increment, right? So, and then we will plug this stuff into the imaginary exponential for evolution on a very short time. I cannot put equality sign, so they just correspond, because we already swapped Lagrangian to Hamiltonian. But if we go forward for a long time in the future, we need to use integral form. So we use total energy that is computed at each point of time for total energy operator. We integrate it and put it into the power of exponential. So this yellow stuff will be evolution operator that helps us to go from the past to the future. So from initial time to final time. The little letter t is not needed in this class at all, but rigorously, generally, if one goes to the next chapter of science, the so-called field theory, there are hypothetical trajectories when a particle goes forward in time, then backwards in time, then forward again, and mathematically it's not forbidden. So this t means that we consider only trajectories that go forward in time. Basically, t means we decline existence of time machine. So, a couple of important points that I missed to deliver last time. So, they are very natural, but it's better to speak them out. So, one can. It is a standard thing that you had in your calculus, and if anyone does computational modeling, one cannot have continuous function. One needs to chop any argument onto discrete points, right? One can assume the timeline as several small time steps. So if you do have our timeline as a summation of little time steps here, there, one can tell, okay, we do have wave function at the initial moment of time in past. And then we apply this evolution operator for the first interval of time. And then we will have the nearest future at time equals delta t1. Okay? Then if you go forward in time, we have the next element of evolution. We take what is the value of total energy at time 2, multiplied by interval of time delta t2, and apply it to what we had before. And then this construction will be future at a time equals delta t1 plus delta t2. And then we can set up a progression of multiplying previous time step by a small evolution operator given a small increment in time. Are you okay with this? Okay. So it is a product of several exponentials. past to the future. What is the product of exponentials? Is exponential of summation, right? So the stuff that we had on the previous slide is equivalent to having a single exponential and putting all this Hamiltonian total energy times delta t into the brackets as a power of this imaginary exponential. And if one adds together function at time t and this delta t, it will be the same as just integral from initial to final time, right? So the time evolution is integral from initial time to final time of the total energy operator, and there is a imaginary unit and Planck constant to make the argument of this exponential in terms of radians. One uses the letter U for evolution operator. I do not know why. I don't know which letter in which language it abbreviates, but it's quite common. Unitary. So it's unitary operator. If one applies it, if one applies evolution forwards in time and backwards in time, just by swapping timeline, one would arrive back to the initial, to the past, to starting point. And this is, so the complex conjugate of this operator, if one replace I to minus I, will just move us backwards in time. And this is, later we will get the definitions of unitary operators. So U probably stays for unitary. Okay, we are done with Wednesday lecture 4 and starting our meeting today. I do not know what to design and how to proceed, but I need some feedback that I haven't lost your attention. I think we will do a little exercise on the board. It's a little less fluid than having micro interviews, but then we will have a confidence that, and I will help. Do not worry. So here is what. Huh?
The slides that I on the Google Drive that are loading in.
A little. I know how to copy paste your name, but I didn't remember it. Can you remind me your name? Ifine. Yeah. So Ifine, did you got the email with materials for this meeting?
When you sent it this morning?
I did send the materials.
This morning?
Yes, this morning.
No, I'm not constrained.
Please look and since you are auditing the course, you are invited to do the same assignments as everyone in class, and in a week from now, on Friday, there will be presentations, 4 minutes long presentation. I think everyone who was in class has already signed up. Everything, there are 2 subjects that are not taken, and you can select them just by filling this Google Slides document. Just put an arrow between your name and the subject that you want to present. Okay. Okay, so we are going to make sure that we are on the same page by doing a little assignment. So here is a summary of what we were talking before. We have past, we have future, and we have a relation operator that drives us from the past to the future. This is a very important step. If we successfully complete it, it will be major point of foundation for the rest of the course. The goal of the very little derivation that I would like everyone in class to come to the board and write a couple of symbols, but it is there is not enough space for it. It's one line derivation, maybe 2 lines. What is going to happen? By now, we were speaking about wave function as a full entity everywhere in the space. And evolution operator applies to the whole wave function, which is very solid, very glorious, but not practical. As humans, without GPU in the brain, we typically focus on one point of information, right? And all calculus that we pass in our careers speak about properties of mathematical objects at a given point of time, coordinate, and so forth. So there are theorems, there are mathematical codes. So we need to jump from this generally philosophically correct evolution of the whole function everywhere. We need to look for the properties of time evolution at a given point of time, at a given point of space. So basically, we need to say what would be the derivative of the wave function over time. And intuitively, it is clear that since we do have this evolution operator, we know what is wave function at the near past and the near future, and we can basically subtract them and see what is the increment. And then we can do the same thing to focus on a given point in space. But let's do it rigorously with some skills and theorems that we borrowed from calculus. So, what do you see on this slide? Switch camera to the board. We anticipate someone to come here. So there are two functions. Both of them formally have time, right? And we need to take time derivative of the wave function over time. Okay. So if there are two functions, what do we do? And please give me the name. How do you call this? Or CHEM?
The product rule?
Product rule, yes. So we take derivative of the first function, keep the second function unchanged, and then we keep first function unchanged and take the derivative of the second function. Let's see. I hope that the next slide is empty. Anna, would you like to help me? And I'll help you. Let's try.
We'll go up there.
You like to draw on screen on the board. Okay. So I'll start and you continue. So ddt u t minus t naught times psi t naught equals to, and then I just apply product rule to your best.
UT.
So I suggest just reduce the single derivative, ddt. Then reproduce the first function. Put another bracket here. And then just rewrite the thing. First function and change it to reproduce third function.
Let's say it's 20 numbers, that's 2 questions.
And now new set of brackets, one upwards, and inside DT simple derivatives applied to the second function. Just psi of T naught x. X, and it's all an argument of the psi single function. That's great. That's great. This is all correct. Please join me up. It's a great call. It is a most important step in the whole class. Is a foundation for the rest of what we are doing. So, what can you say about this object that Anna derived for us? So, suppose that we have a very certain T naught. For example, T naught equals 0. So it is then wave function at T naught is not a function, it's just a constant. What is the derivative of constant? 0. 0. And then it doesn't matter what we multiply by 0. Right? So we remove the second term. Sorry, you had to spend time on writing it. Okay? And now in the second term, we have wave function of the past, and here time derivative of the u. Right? So we just need to find time derivative of the u, and then it will be correct t psi of t over x. And then we hope to get a differential equation that will control propagation of the wave function forward in time. So, yes, you want to help? No, no, come. Emma, he saved you. I was targeting you to go next.
I was wondering why would the wave function be constant? Because when you
It will be constant as function of time. It can have spreads over the space, but as function of time, it is the same. Initial conditions of the differential equation is not changing over time because it is initial condition.
Okay.
So thank you for coming up. I will reset a little assignment. So if we need to find this stuff, right? And the u of t minus t naught is an exponential minus I over h bar. Let's simplify the task. Generally, it should be integral from t naught to t h of t dt. But if we have a very small time increment, we can approximate it as minus I over h bar, h at time t naught times t minus t naught. So please take this information and evaluate ddt of u t minus t naught. If you prefer to work while sitting, you're welcome. It's like a joke. Why are you chopping wood while sitting? Because I tried to lay down and chop the wood and it wasn't successful.
so these are two.
This is a different function, and this is just product.
Okay.
And you can just teach us and say which theorem or which property skill you're going to use.
Well, first we're going to do the chain rule here.
Yes.
So I'm just going to write it as the derivative with respect to time of negative I over h bar h T naught. Minus T naught. Derivative is the same. You want me to do this? Okay.
If you're tired, we can pass on and return to Emma.
You want to do it, Emma? No. Okay.
You'll find some assignment next time.
So
But he did a major breakthrough already, right? So by taking derivative of exponential, the stuff it jumps up front. And here, let's assume that, well, not assume, we know for sure if it is a fixed time, the h doesn't change over time. So it's just
so the derivative is 0.
So we apply derivative only to this bracket. So
okay.
ddt of t minus t naught equals to yeah, but ddt over t minus t naught just one, right? Yeah. Is it clear for everyone? Give me a little signature if I need to comment on this. Or
So you're saying it's just 1 because we're doing the derivative with respect to t naught, t naught.
yes.
Okay, yeah.
Derivative over t naught will be 0, derivative over t will be 1. So we just remove this bracket, remove the symbol of derivative, and this will be an answer. Instead of rewriting, you can just erase unnecessary things. So okay. And yeah, let's. There is one more step, but I want to give this portion of glory to Emma. So let's encourage. Do not be scared. It is much easier, but also important.
I'm not sure where we're going, so.
So we are going to discuss and think, and then it will be a very brief writing.
Okay.
So please identify what is. So the answer consists of product of two terms. This Hamiltonian with constants and the exponential. What is the name of this exponential? Can we replace it to one symbol and tell what it is? If you completely blank, and you can just repeat with yes, perfect. So so this one can be replaced by u. So better right equals 2. And then reproduce this term.
That's right.
Excellent. Please join me in thanking Emma. Well, I like the way how you enthusiastically support each other. And there is one little step, which is very simple mathematically. Sorry, James, that I do not give you a big challenge, but please comment and help us. So here is probably this little spot will be sufficient to give the whole answer. And let me explain what we need to do next. Our original goal was to find time derivative of psi, right? And we expanded, blah, 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 and we found that it is time derivative of u operator times wave function at initial time. Right? Now we need to plug in the collaborative discovery of Garrett and Emma and put into the equations that Anna has derived for us. So it equals 2, and then plug in the answer. order matters. Maybe I suggest please erase and start over. In quantum theory, as we will learn either today in the remaining minutes or next time, order of things is dramatically important. If you swap order of terms in a product, you will get a different answer. So do not swap the order unless you are specifically instructed to do so.
So because they're matrices.
Exactly. Super. Okay. That's correct. That's correct. Let's please join me in thanking James. Your name starts with I. Yeah. Can you repeat it once again? If I look. Yeah. If I look. Okay. If I please come and help us.
I'm trying to understand concepts.
You'll be able to. It's not a big challenge. Okay. So everyone is following what we are doing, right? So we are going to simplify the equation that was discovered by James. So mathematically, what you are going to do will be very simple. We need just to think before writing. So the main property of evolution operator that it progresses, it changes wave function of the past to the future. Right? So I will even write it down once again. It was shown in slide. So if you have, I'll put it probably here, and then you will so psi naught past psi t, which is bigger than t naught x, and here is ut minus t naught. So we go from past to the future. Now, can you combine this equation and the answer by James? And this little spot will be more than enough to write the answer. So you see, there is evolution operator, and there is a wave function of the past. If you combine these two, what do we get? Anyone sees what we're going to obtain? No. So u of t minus t naught, psi of t naught. So can we replace this combination by this? Rewrite this part, and instead of this two, write wave function of the future.
Excuse me. Okay. This.
This again. So this symbol is this symbol. This symbol is this one. They all together can be replaced by this symbol. So you can rewrite this part, and instead of this one, write this one. Thank you so much for being brave and coming to help us. Times. Yes, yes, thank you, Philip. As a team, you all deserve Nobel Prize in physics. You did derive Schrodinger equation. Let me. We don't have more time, so I'll just rewrite it without a computer. So ddt dt of psi equals minus I over h bar h psi. Right? Time derivative of the wave function is equal to total energy operator applied to the wave function. So this is very powerful. Like 90% of modern science is based on this equation.
And is that Hamiltonian a matrix or is it just a scalar?
This, I do have an answer. So, Hamiltonian is either a differential operator or a matrix, depending on which representation do we use.
Differential operator like a gradient or a curve?
Yes, exactly. And this is the main part of one of the postulates, so that regular observables, regular things from our like physics classes, like position, momentum, angular momentum, are replaced by gradients, by a certain vocabulary, by a certain dictionary. And now this way we come to from classical to quantum mechanics.
Okay, so which type of differential operator? Is it just a gradient or is it like a?
Oh, you want me to reproduce the whole dictionary in -1 minute because we are over time. Last slide of this lecture includes brief beginning of this dictionary. You will find it. And no class on Monday. On Wednesday, we'll just cover what is missing here and then go forward.
You sent us the lecture slides for today?
I believe so.
Yeah, you did. Okay.
Like, looks like the sum of the particles.
Yes.
I guess rotation. What are we supposed to like have on it?
Suppose you live 140 years ago and you want to defend to the community a postulate for the mechanics.
So we're supposed to like basically teach the concept.
Yes. Yes. Suppose that you are teaching not to us, but to someone who
Okay,
doesn't.
I don't know if there's like a specific outline or just wing it if we want.
And keep in mind that it will be only 4 minutes per person, so you cannot do whole.
Yeah,
It's like couple, 2-3 slides in PowerPoint.
I'll try to make it 4 minutes.
Super, super. Well, have a pleasant and happy Labor Day. Meeting is done. Everyone is welcome to depart and disconnect. And thank you for the great help with these derivations.
You don't have the other. And all, is this all like real derivatives?
So derivatives.
Not partial derivatives?
Well, time to time it's on the slides. It's okay to have it as regular derivative. But when we will have multi-dimensional x and y, there will be part in respect to the projections. When we use the dictionary for the differential operators, there will be partial.
So where do we put this term? We solved for the derivative of u, but the derivative of
Lesson 4.
oh, is it over there?
Yes.
Just glance. I think I have my head right. Sorry.
Should there be a minus here?
No, it's product. It's product multiplication. Same as here.
Oh, that's a problem. Oh, I thought there was a, oh, yeah, because that, yeah, so just a basic differential equation.
Right.
Well, simplified to be a simple differential.
H is not a constant. It will be, say, it depends on multiple variables and then have a differential operators in respect to x, y, z. Therefore, we will solve the differential equation.
Okay, so the total derivative of time equals to some. I think this is differential operator of the wave function.
Exactly.
That option, or
That's correct.
is it so the Hamiltonian isn't that like it's H I over 2m or no I over 2m something like that, and then it's like divergence of the gradient or something.
Yeah.
So basically, it will just be like
we will spend some time.
What does that mean?
So if you choose
something.
So it's pretty like it's let me show you the slide. It'll leave much easier pressure. It's fine. So like it looks like the H with the little hat. I'm assuming is that what the same H here? Is this little
H bar?
Yeah, is this little
H
H hat is this one.
Okay, it makes it right. So it basically means negative h bar squared over 2m, and then times that stuff outside. This is the operator, so basically we take the sum of each of the partials, square them, and add them together. Or second partials, the sum of the second partials.
Yeah.
I guess you can say. Right now, it looks scary, but
Yeah.
there is this very clear human-oriented way to rederive any of those parts of this vocabulary. And
Okay,
we are going to go over it.
so all the readings that you sent us, what do they all kind of go over? Just
They provide philosophical concepts behind Schrödinger equation.
behind
Behind
all of
yes.
this, okay, not in front of.
The foundation. That's
Yeah.
when we get Schrödinger equation and we understand and believe it, we can neglect this.
Okay.
They just explain, if you do not believe it, if you have doubts that it is correct, or if it will be helpful, electronics research, electrons as waves, then read those.
Because it's our job to prove it well. Right?
I mean, basically.
That's science.
Like it. I feel like I need a few more years of physics. Yeah.
No, we got this. We got this, James. We can do it.
I mean, I bet.
The James equation.
Yes. I just thought if I will be in a boring way showing the slides, everyone will be falling asleep and not engaged.
Yeah, definitely.
I hope that
This was.
I mean, I enjoyed it. I was like,
Yeah.
if you chose me to take the group, I would have had fun with it.
Yeah.
Even if I would have gotten the wrong part at the time, so. Energy operator. So the energy operator. It's like a matrix, I suppose.
so the conversion between differential operator and the matrix is a subject of additional discussion. We will do it, but it is not like 1 minute.
Okay.
So it needs additional concepts that
So
we
applying a matrix would be the same to a vector would be the same thing as applying a differential operator to a
absolutely
scalar.
correct. Yes. Yes.
Okay. Good question.
Yeah.
Okay.
So.
Second.
Yeah. If you agree to take it. Yes, no more than 4 minutes.
Not, just. No, it's just to make it clear I understood the differentials. I don't really get the Hamiltonian.
Yeah, assuming psi is a scalar, I think it works.
That's okay.
with The divergence of the gradient. The wave function.
Yeah, well, that's psi.
Yeah,
Okay.
that's psi, yeah.
Okay, I didn't.
So have you done differential?
I'm in different right now, so I've solved.
Simple ones. Like math 40 material mode.